Hello everyone, welcome back. In this lecture, we shall see the introduction to CFD basics. We shall focus our study on CFD and CHT, that is conjugate heat transfer analysis required for thermal simulations. Introduction to CFD. As we know, CFD is a simulation technique used to numerically solve and analyze fluid flow, heat transfer and related phenomena. What it does? It solves the governing equations of fluid motion, that is Navier-Stokes equation and energy equation, in addition to continuity equation. It predicts how the fluids, that is liquids or gases, behave under different conditions. We can visualize the flow patterns like pressure, temperature, velocity and other key parameters through CFD. The main advantages are it reduces the experimental cost and predicts the performance under various conditions. We will not be able to do experiment under different conditions, whereas in CFD you can predict the performance under different conditions. Next we shall see the governing equations. The first one is continuity equation or mass conservation equation. The purpose is to ensure mass is conserved in the flow. Okay, let us see the equation. The equation is given as dou rho by dou t plus del dot rho v is equal to 0. Here rho is the density and v is the velocity vector and t is the time. So the first term dou rho by dou t represents the rate of change of density with time. So this is the unsteady term. If we are solving a steady state case, then this term will become 0. The next term is called divergence of mass flow or net rate of mass flow per unit volume. It describes if mass is accumulating or depleting in a region. Okay. We know that rho v describes how much mass is moving in a unit area per unit time. Rho av is equal to mass flow rate and rho v represents the mass flow rate per unit area. For steady state flows, dou rho by dou t is equal to 0. And for incompressible flows where the density is constant, we can take it outside and it simply becomes del dot v vector is equal to 0. Role. Even if heat transfer is the focus, the flow field or the velocity field must be accurately solved to compute velocity and temperature fields. This equation represents that mass can neither be created nor destroyed. That is, whatever mass enters in a control volume can either stay in it or it can leave. There can be no gain or loss in the mass inside the control volume. Next we shall see the momentum equations. This is commonly known as Navier-Stokes equation. The purpose of this equation is to describe the conservation of momentum. This is based on Newton's second law for fluids. Let us see the equation. Here the terms rho represents density, v represents velocity vector, p represents pressure, mu is dynamic viscosity and f is the body force, example gravity force. Here the terms on the left hand side represents acceleration and on the right hand side represents force. This is simply put, force is equal to mass into acceleration. Okay, we will see the terms one by one. The first term dou v by dou t represents the unsteady acceleration, that is change of velocity over time. And the next term v dot del v represents convective acceleration, that is change of velocity along a particular flow path. So the terms together represents the total acceleration. Okay, and on the right side del p represents pressure gradient force, the next term represents viscous force and the last term represents body force, example gravity force. Okay, the momentum equations are solved in three directions, that is x, y and z directions. Therefore there are three equations in total for the momentum equations. The main role for this equation is to define the velocity field, which is crucial for convective heat transfer. Okay, finally we can see the energy equation. This is the key equation for heat transfer analysis. It includes the temperature term. The main purpose is to govern the conservation of energy, that is first law of thermodynamics. The general form of energy equation is given here. The term T represents temperature, Cp is specific heat capacity, K is the thermal conductivity and phi is the viscous dissipation and S is the source term, that is heat generation. Okay. Interpretation. The left side term, that is del T by del T, del capital T by del small t represents the unsteady term. It captures the transient effects. For steady state flow, this will be 0. The next term v dot del T represents convection term, that is temperature changes due to fluid motion. And in the right side you have got the first term conduction term or diffusion of heat and the next terms are viscous dissipation and S represents the source term of heat. So this is all about energy equation. So in total there are 5 governing equations, one for mass, 3 for momentum and 1 for energy. So solving these equations we will get the CFD analysis output like pressure field, velocity field, temperature field, etc. Okay. Next we shall see the key steps in CFD. There are major 4 steps involved in CFD analysis. The first one is pre-processing, the next one is case setup, followed by solver execution and post-processing. Pre-processing includes geometry creation or cleanup of any existing geometry or imported geometry, and then mesh generation. Next, once the mesh is generated, we will define the physics and material property in the case. We will specify the boundary conditions, turbulence models, solver settings, etc. and we will load the case for solver. In the solver, we will run simulation, monitor the convergence and check the solution progress. Finally, once the solution is complete, we will take it to post-processor and we will visualize the plots, graphs, analyze the results and extract the data for comparison. So these are the main steps in CFD analysis. Alright, we shall see about meshing and boundary conditions in the next lecture. Thanks for watching this video. I will see you in the next lecture.